In this video, we're going to see how to calculate the change in entropy of the system for a chemical reaction. In the videos that we have seen prior to this, we have learned the second law, and then we have defined thermodynamically entropy, and we have seen how the thermodynamic definition of entropy can be used to understand changes in entropy in gas expansions, heating, cooling processes, phase transitions, and we've also applied it to the surroundings. But of course, in chemistry and in the life sciences, something that is of most important thermodynamically would be calculating the change in entropy in a chemical reaction, and that's going to be the body of this video. Okay, so the way that I'm going to explain this to you is by simply writing a chemical reaction and going through the concepts that we use to calculate the change in entropy. The chemical reaction that I've chosen is a simple combustion reaction of natural gas, which is mostly methane. So methane is just CH4 gas, which we can burn with oxygen gas to generate CO2 as a gas, and then water, which if we run this combustion reaction under ambient conditions, 298 Kelvin, and 1 bar of pressure, then water would be a liquid. Alright, so the question is, well, how do we calculate the change in entropy in the system for this chemical reaction? First things first, something that is quite easy to do and convenient is to actually predict what the sign should be for the change in entropy in this chemical reaction. Now we know that gases are far more entropic than liquids than solids, so just by visual inspection and just tallying up how many moles of gases you have in products and reagents, you can conveniently anticipate what the sign should be. For example, notice that in this chemical reaction we have 3 moles of gases in reagents, but only 1 mole of gas in products. Right? There's 2 moles of products as a liquid, but again, liquids are far more ordered than gases, so you really can generally just do this estimate based only solely on gases, right? So you go from 3 moles of gases in reagents to just 1 mole of gas in products. You're losing this order, right? So the change in entropy that you have for this chemical reaction should be negative. Okay, so then the question is, well, how do we actually calculate that? Well, to do this calculation, we can leverage the notion that the change in entropy in the system is a function of the state of the system. In this case, the system is a chemical reaction, so the initial state is going to be reagents, the final state is going to be products, and because the change in the entropy is a state function, you only need to know what the entropy of the final state is, and then what the entropy of the initial state is, you take the difference, and that is the change in entropy in the system. Right, so in our case, the final state is products, and the initial state is reagents, so really the change in entropy in the system, that chemical reaction, is just going to be the difference between the entropies of products and reagents. Okay, so to put that in a formula, what we can say is that the change in entropy, and usually these entropies are going to be per mole under standard conditions of 1 bar, that's simply just the sum of the entropies of products, which will be molar and standard, minus the change in entropy, the entropies of reagents. Right, so, well, this seems simple enough. The question is, where are these molar entropies coming from? Do we have values for the molar entropies of liquid water and CO2 and oxygen gas and methane? Of course, oxygen is molecular oxygen, right? So do we have molar entropies for all those species, and if so, where do they come from? Okay, so here to explain where these molar entropies come from is instrumental to remember how we did something similar when we were talking about enthalpies in the first law. We actually learned how to calculate enthalpies using for chemical reactions using the method of enthalpies of formation. There, we simply just set a 0 for the enthalpy of formations of the most stable allotropes. of constituent elements, and then we simply based the enthalpies of any species like water, like CO2, off of that sea level, which was the most stable allotropes, the zero of enthalpy, and that gave us tables with enthalpies of formation that we could use in an equation that was very similar to this. In the case of entropies, we actually don't have to use that trick. We don't have to arbitrarily set a zero somewhere, because the third law of thermodynamics tells us where that zero is. Okay, so what is the third law of thermodynamics? Well, the third law of thermodynamics simply asks the question of, well, suppose that you have a substance like oxygen or water or methane, whatever, doesn't matter. The question would be, is there somewhere where you actually would have perfect order, which means zero entropy? And then if you stop to think about this for just a little bit, you can quickly realize that because entropy is related to the mass dispersal and energy dispersal, you can make the entropy zero. If you remove all energy, that means that you go to 0 Kelvin, right? So there's no energy dispersal at all. And then if you organize all the mass in a regular lattice, as it would happen if you have a perfect crystalline substance that is pure. Okay, so that is actually the third law of thermodynamics. The entropy of a pure, perfectly crystalline substance at 0 Kelvin is 0. Okay, so that's actually what this tells you. Right, so the molar entropy of any substance that is pure and crystalline at 0 Kelvin, right, that is equal to 0. Okay, so that's the third law. The question is, well, how is this useful to calculate the change in entropy in this chemical reaction when the chemical reaction takes place at 298 Kelvin? Well, so the idea then is that we simply have to, yes, based off this zero, we simply have to calculate what the entropy of a substance would be at the temperature of interest, 298 Kelvin, and that would be that. Okay, so to see how this works out, we can actually then take any of these reagents or product species that we have to just see how we go from the third law to actual useful entropies that we can utilize to calculate changes in entropy in reactions at temperatures that are of interest, like 298 Kelvin. Okay, so here would be kind of the idea. If we take oxygen, for example, the idea is that we know what the entropy of oxygen would be if this was a perfectly crystalline substance, that means a solid, okay, at 0 Kelvin and pressure of 1 bar here. That is 0. That is what the third law of thermodynamics is. But of course, we're interested not in that. We're interested in oxygen, which is a gas in this chemical reaction, at a temperature of 298 Kelvin and a pressure of 1 bar. Right. So again, if we know how to go from here to there, right, then we would know what the entropy of that molecular oxygen is in the gas phase at 298 Kelvin, and that is what we need to compute the change in entropy in this chemical reaction. Okay, well, so notice that this is not difficult. This is actually just a combination of processes that are going to take you from here to there, right? Notice that there's a couple of things that are changing. Right? Notice that from the solid you go to the gas, okay? And notice the temperature is also changing from 0 Kelvin to 298 Kelvin, right? So notice that this is just a combination of heating, right? The temperature changes, and phase transitions, where you will go from the solid to the liquid to the gas. Okay, and just at 1 bar, we can just write here that the freezing point is 54 Kelvin for oxygen, and the boiling point for oxygen at 1 bar of pressure happens to be 90 Kelvin. Right, so then the pathway is very clear. First, what you do is you start with solid oxygen at 0 Kelvin, no entropy, the entropy is 0, and then you simply heat that oxygen up until it's a solid, but at 54 Kelvin. You simply bring this to the boiling point, to the freezing point. After that point, and we know how to calculate that, right? The change in entropy is just the change in entropy in heating, and we've done problems to know how to do that. At 54 Kelvin, though, then there's a phase transition in which the solid oxygen turns into liquid oxygen. And we know how to calculate that change in entropy as well from earlier problems. Right, so after that you get liquid oxygen at 54 Kelvin. You continue to elevate the temperature, so that is now heating of liquid oxygen until the temperature becomes 90 Kelvin. So then you've brought liquid oxygen to the boiling point. Now you evaporate or vaporize that liquid oxygen until it turns into gas oxygen at 90 Kelvin, and the final step would be to simply calculate the heating of the gas from 90 Kelvin to 298 Kelvin. Right, so to calculate this change in entropy and therefore know what the total entropy of oxygen is at these conditions, which you need for the reaction, you would just need five steps, which can be calculated. Right, so instead of calculating each one of them and just showing you the nuts and bolts of this, we're simply going to draw a graph that is hopefully going to be useful to you. Right, so those 5 points can be illustrated as follows. This is how the molar entropy of oxygen changes, and we can use here units of joules per mole Kelvin under standard conditions, which is 1 bar, as a function of temperature. Okay, and the important points here will be 54 Kelvin, which I can draw here, 54 Kelvin, that is where you have melting of oxygen. And here you would have 90 Kelvin, which will be boiling of oxygen. And here is 298 Kelvin, which is what you're interested in. Okay, so this is the temperature axis in Kelvin. Okay, so notice that you start at 0 Kelvin, right? That is your starting point, and you actually know what the value of entropy is. This is the third law. At 0 Kelvin, the molar entropy of a perfectly crystalline substance is 0. Okay, so that's actually where you start. And then what you do is simply heat that solid until it reaches 54 Kelvin. And then at this point, what you actually have is a phase transition, which is fusion. At that point, notice that phase transition is isothermal, right? So the entropy grows, okay, but the slope is actually infinity because the temperature is not changing. It's an isothermal process, right? So that is the change in entropy due to fusion. And this change in entropy from here to there, that is just simply heating solid oxygen, right? But now you have the liquid, and then what happens is that you have to evaluate or change the temperature of that liquid until you bring it to the boiling point, which is 90 Kelvin right there. So this line corresponds to the heating of the liquid from 54 Kelvin to 90 Kelvin. At this point, you're ready to boil that oxygen, so the entropy will increase. Okay, no change in temperature, that is just the boiling or vaporization. And at the end, here, at the end of this process, you just have gas oxygen at 90 Kelvin, and the only thing that you have to do is just bring it to your temperature, which will be 298 Kelvin right here. And this step simply corresponds to heating of the gas. Okay, so there's 3 heating steps and 2 phase transitions. Simply calculate the change in entropy in all of those, and you will get what the molar entropy is for that oxygen, and this number is known. Turns out that number happens to be 205 joules per mole Kelvin. Okay, so like this, you can actually proceed with any substance of your choice. But you can do the same thing for methane, you can do the same thing for CO2, you can do the same thing for liquid water. And what that means is that you're going to have thermodynamic tables that are going to provide these absolute molar entropies for all substances that you're interested in, generally at 298 Kelvin under standard conditions, which is 1 bar. Okay, so then if you have those values, then calculating the change in entropy in the chemical reaction is straightforward, because the only thing that you have to do then is just add up all of the entropies of the products, multiply by the stoichiometric coefficients, and then subtract from those the entropies of the reagents, methane, in this case methane and oxygen, multiply by the stoichiometric coefficients, and that difference is just simply the change in entropy in the system, which will be the chemical reaction. Okay, so just to wrap up this video, we have seen that how to calculate the change in entropy in a chemical reaction, and we actually, most of the video has been concerned with how do we actually obtain the absolute molar entropies that are required in that calculation of the change in entropy in a chemical reaction. As it turns out, those molar entropies are based off the third law of thermodynamics, which tells you that the entropy of pure crystalline substance at 0 Kelvin is 0. From there, it's very easy to then estimate or calculate accurately what the absolute molar entropy of a substance would be at the conditions that you want, and then from those you can just plug the entropies in this equation and obtain what the change in entropy is in a chemical reaction.